I would like to welcome you to the Getty Conservation Institute. This seminar will take place in English and in Spanish. On the bottom of your screen, you will be able to find an icon where you can select in what language you would like to follow the presentation. Today, we will have 4 panelists, and at the end of the presentation, you will be able to ask questions. Please send your questions throughout the presentation in the question and answers box that you will find on your Zoom screen. The panelists that we will have today are the architect Susan McDonald. Susan McDonald came to the Getty Conservation Institute in 2008. Susan studied architecture in the University of Sydney. She also studied at York University. Now she supervises 25 international projects with Getty. And she works in investigation on the field, and then we will work with Claudia Cancino. Claudia is an architect from Peru, and she works with the organization Ricardo Palma in Lima. She also has architecture studies in Peru, and she also has an advanced certificate in conservation by the University of Pennsylvania. In 2002, Claudia specializes in projects through earthen architecture. We also have the presentation of the engineer Daniel Torrealba. He is a professor and works in the university in Peru, where he has worked since 1975. He graduated as a civil engineer in 1972 and then received his master's in the University of LA in 1980. He is also a member of Iconos Peru. We will also have the participation of Paulo Lorenzo. He is an engineer and professor of civil engineering and engineering in Portugal. He works in sustainable studies and where there are 250 researchers. Dr. Lorenzo has a lot of experience, and he is also a specialist in structural conservation. And he has worked on more than 100 monuments and 17 from the patrimony of UNESCO. He is also a leader and coordinator of the European Masters for Historical Constructions, and he has worked with students from over 70 countries. Now we will initiate the different presentations, and we would first start with Susan McDonald. Welcome, Susan.
Well, hello, and a warm welcome from the Getty Conservation Institute. In case you missed the instructions at the beginning, this webinar is being undertaken in Spanish and in English. And if you choose your language channel from the bottom of the screen, you can choose which language you would prefer to listen in. So we are a Los Angeles-based nonprofit organization dedicated to advancing the practice of conserving cultural heritage internationally. And our work involves research, field projects, the creation and dissemination of literature, and training. And this particular project that we're hearing about today involves all of these different modes of work. For millennia, humans have constructed buildings of earth. Earth has been employed in a wide variety of geographic context and climatic conditions, and the construction ranges from small, humble vernacular housing to large, spectacular public buildings and urban settlements. It is one of the most ancient and sustainable building materials. Given the material's global preeminence and cultural significance, For the last 30 years, the Getty Conservation Institute has engaged in projects and initiatives to advance the field of earthen conservation. Given the prevalence of earthen architecture in earthquake-prone regions of the world, as far back as 1990, the GCI established the Getty Seismic Adobe Project, or GSAP, to develop and test techniques to prevent the collapse of initially Californian historic earthen structures during seismic events. In 2009, the GCI initiated the Seismic Retrofitting Project, or SRP, as you may hear today, with the objective of advancing that GSAP techniques to better match the equipment, the materials, and the technical skills that are available in a much broader range of places with historic sites. And we focused this work in Peru, a country with a rich earthen heritage. Today's event celebrates the work that we've been undertaking in collaboration with the Ministerio de Cultura del Peru, the School of Science and Engineering at the Pontificia Universidad Católica del Peru, and the University of Minho. This work involved the design, the testing, and the implementation of seismic retrofit techniques and maintenance programs using locally available materials. These techniques will improve the structural performance and safety of earthen buildings while minimizing the loss of historic fabric, and thus sustain this invaluable heritage. In order to ensure the efficacy of these techniques for a range of historic building stock, we identified 4 Peruvian historic earthen building typologies that are found right across Latin America. And over the last 12 years, the SRP has produced a total of 6 publications resulting from the work of the project. They cover topics from damage assessment of historic earthen sites after the 2007 Pisco earthquake, which is what started our work in Peru, to detailed construction assessment and testing and modeling results of the historic earthen buildings that we selected for further study. The final outcome of this project, which is currently in development, will be guidelines for the seismic retrofitting of historic earthen sites. Today's webinar presents the publications that are now available in English and Spanish to download for free from our website. I'd like to take a few moments to thank our really incredible team who are responsible for the work, and you'll be shortly hearing from and hearing about. To our highly skilled engineers, Dr. Paula Lorenzo and Dr. Danielle Torrealba de Avia, who have brought their superior understanding of historic construction, their creativity, and their practicality to this endeavour. It really has been a journey, and we cannot think of greater professionals to be working with us on this. To my Getty colleagues, Cynthia Godlewski and Chelsea Bingham, who so ably shepherd our publications through to realisation, a huge thank you. And to my wonderful GCI team, Elena Macchioni, and our dynamic project leader, Claudia Cancino, who's largely responsible for this work, I want to say a huge thank you as well. This team has worked so very hard over such a long time to drive, to design, and to steer and fulfill the very large ambitions of this project. And it's my great privilege to be able to work with such consummate conservation practitioners. And I, for one, am very proud of the work that's been achieved here. I would now like to pass over to Claudia Cancino, who will introduce the first publication on the assessment of prototype buildings selected for our work. Claudia.
Thank you, Susan. Today, I am going to present the first 2 publications of the Seismic Retrofitting Project, the 2007 Earthquake Assessment Report, and the Prototype Construction reports. I also would like to acknowledge that apart from our wonderful partners, Ministerio de Cultura del Perú, Pontificia Universidad Católica del Perú, and TecMinho, the University of Bath and University College London collaborate with this project at the beginning in 2010 and 2012, respectively. So you all have heard that I'm Peruvian, and probably you all know that Peru has a variety of earthen sites, starting from the pre-Hispanic period. And actually, in the last couple of years, researchers have discovered the oldest earthen architecture on the north coast of Peru, at the site of Los Morteros in the Chao Valley in La Libertad in Peru. The site was constructed with ancient earthen blocks carried from natural clay deposits by floods, probably caused by an early El Nino. And the bricks are dated around 3,000 years before our current era. So probably this is the oldest earthen architecture in the Americas. But from there, Peru has developed amazing sites, starting with Huaca de la Luna and Huaca del Sol in Trujillo, as well as the site of Chan Chan. And then the use of this material didn't stop with the arrival of the Spaniards. The Spaniards actually adapt the techniques and improve the techniques to make them seismically resistant. And earthen architecture is something that is currently present in Peru and is used for the construction of modern houses. So, but I also would like to stop a little bit here in the history of Peruvian architecture to talk about these two very important fellows that you can see here on your slide. Don Melchor Portocarrero Lasso de la Vega, also known as Conde de la Moncloa, was probably one of the first authorities in the Americas that create a building code in Peru. And what happened is that, in Lima, we had during the Viceroyalty period 3 important earthquakes, one in 1687, the second one in 1699, and the third one, a very famous one, the one in 1746. And in Cusco, there were also very famous ones that were registered. And the picture that you see on the right side of your screen is from the earthquake in 1650. That it's a painting from Alonso de Monroy y Cortez, and it actually shows how, the damage of this. The damage on the sites after the 1650 earthquake. But going back to Conde de la Moncloa, he was the first one that created a sort of building code or norm after the 1699 earthquake in 1701, where he actually mandated that all of the second story floors of the houses in Lima need to be constructed in Quincha. And then, some of the buildings follow these norms. Some of other buildings didn't, particularly the churches. They continue building their vaults and domes in brick, and they suffer the consequences since a lot of them were destroyed, including the Cathedral of Lima after the 1746 earthquake, where famous Don Jose Antonio Manso de Velasco, also known as Conde de Superunda, had to deal with the disaster a year after he arrived to Peru. And he actually hired a mathematician, a professor of mathematics from the University of San Marcos in Lima. He hired him to evaluate the damage that the houses in Lima and churches in Lima suffered after this earthquake. And Godin came with a series of recommendations that actually shaped the construction techniques of the Viceroyalty period. So Godin suggested the use of mud, cane, and adobe instead of limestone or brick as construction materials. The use of quincha walls, as Conde de la Moncloa has suggested a few years earlier, an increase on the width adobe masonry walls, as well as the buttresses that normally you can see on the earthen churches in the Andes. So, so Peru is known not only for its rich and diverse earthen architecture, but also because of the evolution of the techniques to adapt to seismic events. So this evolution during the Viceroyalty period didn't stop during the Republican period. And there were a lot of academics that actually study these techniques in schools of architecture and engineering. And particularly starting in the 70s, there were a group of engineers at Católica University, as well as the Universidad Nacional de Ingeniería, who actually started studying the use of earth as a building material. And you can see here an image of the 70s when the laboratory of the Pontificia Universidad Católica del Perú was inaugurated. And then at the end of the slide, you can see the new generation of engineers that are actually bringing a series of techniques to understand the structural behavior of earthen buildings around the country. So there is a tradition in Peru to adapt and design retrofitting techniques that has gone over century. So on August 15, 2007, around 6:40 p.m., a very strong earthquake occurred in Peru. The earthquake was described as having two strong motions and affected the sites of Lima, Ica, and Huancavelica, as well as parts of Ayacucho and Junín. And then vernacular architecture, concrete and masonry buildings, damages were recorded there, as well as damages even in the Pan American Highway. So according to SISMIT, that is one of the institutions in Peru that records the earthquake measured had a magnitude of 7.9, an intensity of 7. The epicenter was in the ocean, as shown in the slide, and it was around 40 kilometers depth. There were around 355 aftershocks, 519 fatal casualties, and there were around 58,000 buildings that were completely in ruins. Unfortunately, Peru also lost one of the most important buildings from the Viceroyalty period, that is the Church of La Compañía, that was built around 1650, and it was completely demolished a day after the earthquake. So when this happened, Getty was called by, at that time, the Instituto Nacional de Cultura del Perú to go to the site and evaluate the damage of these of some of the sites. And for us, it was actually an opportunity to understand why these buildings that over centuries have adapted and stand earthquake have failed so terrible during this earthquake. So after a visit that happened in November of 2007, that was composed by around 12 national and international experts, one of the conclusions was that location had a lot to do with how the buildings perform. So here we can see that, for example, the Church of Umay or the Church of Guadalupe are located over alluvial deposits that you can see here in gray, and those are not actually the best soils to stand earthquakes. And similar happens with the Cathedral of Ica. And just for your information, Tambo, Colorado, who is an Inca site that actually has stand a series of earthquakes, is located in a different type of soils. It's at the base of a rocky formation that you can see here in orange. So location had something to do with how the buildings perform. Another conclusion was that for sure the buildings suffer from lack of maintenance. We were able to record termite damage on wooden trusses and cane reeds, particularly at the Cathedral of Ica, beetle damage on adobe blocks and mortars, as well as brittle leather straps that were the ones that actually connect the cane to the wooden structure and allow the mud mortar, the mud plaster to be connected to the whole structure. So another conclusion from that visit was that there were a lot of non-compatible previous interventions. The most common one is that the roofs of the churches, the vaults and the domes were actually in most of the cases covered with a layer of cement, probably to prevent some sort of rain entering the sites, and that actually increased the weight of the roof and had an impact on how these buildings behave during an earthquake. In other cases, as you can see, they had interventions like these concrete porticos that were inserted into adobe walls. And of course, after the earthquake, the only thing that was standing was the concrete structure, and the historic adobe walls had failed due to the difference in pounding during the seismic event. So these type of interventions were the ones who create a lot of damage on the historic sites. We also try to understand how certain elements behave during the earthquake. So we witnessed a shift or total collapse of domes. And that had to do with what we explained later, that the wooden connections were actually heavily deteriorated. So and that's the reason why a lot of these domes shift or collapse, as well as the bolts in many of these earthen sites. So it was a combination between the weight of the roof as well as the lack of functionality of the connections that create all this damage. We also witnessed a lot of out-of-plane collapse due to the lack of connections between the different structural elements, but we also witnessed some sort of a torsion effect here in one of these very interesting columns that you could see in one of the haciendas in the region. So all of this information was actually compiled thanks to some of the international experts that traveled with us. And this was the first publication from the seismic retrofitting project that now you can find in English and in Spanish at the Getty website. So with this publication, we started the seismic retrofitting project that had the objective to design low-tech seismic retrofitting techniques using appropriate materials and local expertise for Peruvian historic buildings, that prototypes that have the potential for a wider implementation in the Americas. We wanted to test and model the scientific that demonstrate the validity of these techniques, obtain the national recognition, develop a model implementation conservation project, and the final outcome, as Susan has mentioned, are the guidelines with an emphasis on maintenance programs. So the first thing that we did was to select, first to define some sort of a prototype that we could find in the region. And then from there, visit a series of sites and select the ones that were more appropriate. So the 4 prototypes that we defined in the region was first, the typical residential house in the historic center that has the first floor made of adobe, and the second, and in some cases, the third made of quincha. The second typology was the typical church ecclesiastical building from the coast that had thick adobe walls, and it has vaults and domes made of sort of quincha as the roof. The third typology is another ecclesiastical building that you can find in the Andes. That is basically a building with thick adobe walls and a truss roof, and in most of the cases it has wall paintings and interior. And then the last typology was a residential building that you could find in the historic centers, also in the Andes. That a difference from the residential buildings in the coast. These are made of 2-story adobe walls and a truss roof. So we based a series of sites and we evaluated them according to historic value, its significance, if some of them had interventions or not. And we came up with 4 buildings that became our building prototypes for further study. The first one, as a residential building from the coast, we had Hotel Comercio in Lima, that is property of the Ministerio de Cultura del Perú. As an ecclesiastical building on the coast, which we select Iga Cathedral. As a residential building in the Andes, we select Casa Arones. And then as an ecclesiastical building in the Andes, we select the Church of Santiago Apóstol de Cumutambo. So the Hotel Comercio is a building made of thick adobe walls in the first floor with some brick around the openings, and then quincha structure in the second and third floor. It has 2 patios, as any of the casonas that you can find in the historic center of Lima. And we went through all the development of the architectural drawings, and we select some areas for further exploration. We were able also to perform a structural assessment of the site, but also use the thermal camera to be able, for example, in this case, to identify the wooden post of the quincha elements. All this research allow us to create a series of architectural drawings and details that help us to understand how these buildings were put together and help the engineers to later design the proper testing and modeling. Ica Cathedral, it was one of the sites that was heavily damaged by the earthquake. It's also located at the historic center of Ica, right more or less in front of their main plaza. It unfortunately suffered from partial collapse of the vault. And this photo that you see here of the dome was taken a few months after the earthquake, and you can see the dome is still in place, but there was another seismic event in 2009, and that was when the dome fully collapsed. So for the Ica Cathedral, we also did all the architectural drawings, the structural evaluation, and the proper prospection. We also use the thermal camera to understand the location of the wooden arches, as well as try to understand the level of deterioration. And also it allows us to understand how these amazing wooden structures were put together. We also discovered that Ica Cathedral has a very similar construction technique that the Cathedral of Lima, which make it even more significant. So we were able to understand the details and the dimensions of this structure that were later served for the analysis that the engineers are going to explain later. We also had select Casa Arones at the historic center of Cusco. This is a typical house of the Andes with 2 adobe story building with a truss roof. We also did all the architectural drawings of and the structural analysis of the house, and we were able to understand all the details of how these typical residential buildings were put together. And last but not least, we also study the Church of Puñutambo, that is 2 hours southeast of the city of Cusco. It's a building from 17th century, it's thick adobe walls with buttresses, and has wall paintings from the same period. We did all the structural drawings and the details of this structure. And we also particularly selected because it has wall paintings. We also use the thermal camera in this case, for example, to understand like the crack that you see here in one of the pilasters of the church, that using the thermal camera, you can see actually that the crack that goes all the way around, the structural element. So this is one of the buildings that we were able to develop not only the analysis with the testing and the modeling, but also the construction drawings. And we did this in collaboration with the Ministry of Culture in Peru. And we are able to implement and carry on the work. And this is an image of the inauguration of the church in 2019. And this is a view of the already seismically resistant earthen church of Puñutambo with the conservation of its wall paintings. And we hope to also have an implementation project for Ica Cathedral and Hotel El Comercio soon. So the analysis of all these 4 building prototypes and all of the details are part of this construction assessment report that in this case I put the image of the publication in Spanish, because both publications that I have presented are both for free to download in both languages. The construction report is actually has 2 volumes. One has the analysis of the 4 buildings, and then the second volume has all the drawings and the details of these significant sites. And with this, I'm going to leave the floor to Daniel Torrealba, who's going to explain all the testing that was performed and carried out as part of the seismic retrofitting project. Thank you.
Gracias, Claudia. Voy a presentar la
Thank
publicación
you,
sobre
Claudia. I'm going to present the components of buildings and historic of Adobe in Peru. Like it was already mentioned, there are four prototypes and two prototypes in the coast, and two of them they are located in the Andes region. And in both cases, we have residential and religious. And the objectives of these laboratory testing is basically to provide information about the analysis of all the meetings between the evaluations, the structural evaluation and the numerical analysis and prototypes. And we were in charge of doing these testing that would come about of these meetings. There was a lot of questions between which ones are the properties of the historic materials of these prototypes, and what is the behavior, the structural behavior of quincha that was already mentioned, and the behavior, the traditional reinforcing techniques of wood, like for the from the Ica Cathedral, for example, and if it's eh, even if the traditional techniques of retrofitting that have been applied back then in the constructions from the coastal area like the Andes. So the first thing was that all of these prototypes, all these buildings have like a common denominator, that all the walls are made from adobe masonry. So we would have to, in that case, analyze all the materials that are composed of this historical component. And we were able to have what we were able to do is to do the the seismic retrofitting project and of all these prototype buildings. Like, as you know, there are differences between the composition of the soil fabricated or built by different prototypes. However, nevertheless, when you see the mortar, like from these same buildings, you know, the dispersion is not as large and it's many more closer. Now, obviously, this tells us something about this constructive process. Now, then later we have the compression of the units, the compression strength of historical adobe units. And what we see here is that there are differences between the resistance, the compression that they have, the units from the like the center of Lima in this case, and the resistance, for instance, the units from the Ica Cathedral and the Coliotambo church in Cusco. You see it's double the unit resistance in all these constructions in Lima of the other two places. Nevertheless, when we speak about of the pile of the piles of this difference disappears. Why does it disappear? Because obviously then we would talk about the union with the mortar, with the like we saw the mortise and tenon. Like you see, they're all similar in their composition. This is what allows it and defines the resistance that we already know, all those that we study this, that is defined because of the mortar and the union between the units of the resistance of the units themselves. What you see is this compression test on the wallets. When we look at the resistance throughout these diagonal compressions, we see that, as a matter of fact, when the resistance to the compression is lower than the Ica Cathedral. So then, because of this effect of the units and the mortar. So in all these prototypes, there wasn't just masonry walls of adobe, but it was also mixed with masonry from walls and brick. So what happens when you have a mix between one or the other one? How would that work? But then there is something that was common in all these cases. The mortar was made of either of soil, and these compressions were made mixed with brick with, but you have to understand that this is all made with mortar uh, of soil. And we were able to do these Adobe in order to be able to the Cathedral. And as you can see, there's not really a difference between the contemporary Adobe that has a bit more resistance of the historical one. No, nevertheless, when we mix the materials, Adobe with stone, Adobe with Adobe and fired brick, basically the results are the same like you see in this graph. Now, why? Because of the mortar. The mortar is a mortar, it's a soil mortar in all the cases. And if you could see this, the friction, the internal friction angle, when you don't see really any differences that are significant, right? So these are the conclusions that I had already mentioned before. And in the Ica Cathedral and the Hotel Comercio, one of the important is timber, right? So we also had to analyze, in this case, the timber material, but something in particular, Peru, there is no timber. There's timber in the Amazonian parts, but there isn't in the coast, and the timber from the highlands is different. There wasn't timber when these buildings were constructed. It was very little timber available. So where does timber come? Where do they comes when all these historic buildings that were made in Lima, they come from Central America, by boat to the coasts of Peru. And timber, then we spoke about the Molina University to have this project to see what they have, the resources in order for to do this. And they were able to identify three different types and three types of timber for the Hotel Comercio in the center of Lima, when there was one timber that was the same, and that is cypress. And amazingly, it was a type of timber that they were assured that comes from Africa. I don't know how that could have been the case, because we tried to look historical information, but there was no historical information that convinced us that that could have came from Africa. So we already know the values of the mechanical properties of all of those type of timber. That is to verify later on the analysis of the numeric analysis that we had to do in this case. So in the case of the Hotel Comercio, we see the structural system of the quincha. And if we already know, and everybody accepts that the quincha is very flexible, very resistant out of the systemic, there wasn't anything numerical information that would corroborate this. So what we did was we had these tests in two different panels of quincha that would represent the panel of the second floor and third floor, right? The third story, as you could see you could see to the right there. And it was reproduced exactly the same dimensions of the same timber and the same type of procedure throughout. So these new panels were reproduced, and the difference between the second and the third has a diagonal beam, but the first one has a rigid base in the bottom. It has it was a rigid for the second base and a diagonal one for the third. And we were able to test with these vertical loads and without vertical loads. And what we could see here in the case of the maximum force, the horizontal maximal force in both cases, it was like around between 12, 13, 14 kilonewtons of maximum force. But the most important is not the resistance itself, but the capacity of formation. The structural system, it was such that if we would have had this testing, this cyclical testing, we weren't able to produce these, we weren't able to do these shifts as far as the behavior itself. So if we have like, of a, say a plus minus 15 in the lax phase, it was modified in order to apply 30 centimeters in one direction. And then you can look at the symmetrical curves that you could see of the cyclical curves. And the last one, it has 30 centimeters to the one side. And what we can see is the capacity to resist vertical loads. It's very, very acceptable. And these are the other panels, what you could see, but this is a, a new type of timber. The timber is 200 years old or more. How could it be? And then after thinking about what we could make this testing of the existing quincha, we were able to like take off the wall of in a area where it was collapsed and rebuild it element by element in a structural lab. So we did this, and we had this again, the testing performed with the same characteristics, in this case without the vertical load, because there was only one panel. And we found that the capacity of deformation was basically the same. So it was a grand capacity without reducing its of these resistance of vertical loads, but obviously the maximum value that was able to get, it was able to come to 10 kilonewtons compared to the 13 or 14 that were done in the other reports. But it was very, very acceptable with a quincha of over 200 years old. So these are the conclusions, are the same that we have been talking about. So as far as the Ica Cathedral, the question that was brought up, that this had many connections in timber, like, there are too many, all these parts connected with them. And the thing is, how do they behave? Well, we picked 3 types of connections, as you could see in the graph to the right, a pin and pinned in one of the mortise tenon. And these we tested as far as the connection with the pin. I said monotony to see the maximum capacity of resistance. In the case of the nailed one and the mortise tenon, this was done in a cyclical way. In the case of the mortise and tenon, was done in 2 directions, orthogonal, parallel to the beam and perpendicular to it, more or less to see what was how rigid was it, because what we wanted to know was at the time was how to model these connections
a la flexión, ¿no? En los casos de que se hizo los ensayos cíclicos siempre fueron asimétricos, como este de acá que he puesto como ejemplo. Esto es caja y espiga y la dirección paralela a la viga. ¿Y por qué razón? Porque tanto la conexión clavada como la conexión que tiene caja y espiga, la espiga se sale de la caja, ¿no? Y el clavo se sale de la posición donde está, pero ya no regresa. En ninguno de los casos regresa, entonces se vuelve una conexión que tiene resistencia en un solo sentido y en el otro sentido casi no tiene resistencia. pero esa conexión después se va perdiendo esa rigidez, por lo que se decidió que si había que hacer un modelo de estas conexiones, lo mejor era que el modelo fuera empernado, articulado, ¿no? Entonces, eso era el modelo que mejor representaba el efecto de las conexiones en estas estructuras de madera de la catedral de Ica, ¿no? Por lo tanto, en ninguno de los casos se tuvo una falla frágil, ¿no?
There was never, what we saw is that the connections kept working in a unified manner. When we look at traditional techniques, we have different ways of connecting. If we connect two parallel walls, as you can see here, we would use beams, and this was used a lot in the churches in the Andes. We would use adobe walls of different thickness of 26, 54, and 83 centimeters. Here we would see a vertical support. So you can see here the thicker walls compared to the thinner walls. We see that this increases the resistance. So more or less 20% increase, the same as here. When we look at the thinner walls, it didn't work because the walls were too thin and didn't work. Another important aspect is that you can calculate more or less what the extraction strength is, knowing the surface and knowing the resistance. So since we know more or less the resistance, so with this study, we can see more or less the maximum strength. The other technique, a traditional technique that has been used a lot in constructions in the mountains and also in some coastal structures, is what they call corner keys. You can see it in some of the homes in Cusco. And the objective of this corner keys is to connect two walls to be able to maintain this connection during an earthquake. This study was done taking into consideration, first of all, to separate the corners in two parts. First, to see which one of the walls was giving problems. We wanted to see these corner keys, and this is how we were able to do this diagram on the right-hand side. And then we did it in the lab. We did it in a type A and type B assembly, and the type C is a variation of type B. And here we put some wooden keys to have more resistance if the key is extracted.
capa constructiva, ¿no? Y se
Here
inicia también
you
esta
can see
extracción
the
del
different
sistema, ¿ya? Pero
extractions that we did of the system
sin carga vertical y
without
simplemente
the vertical support.
falla esto de aquí, ¿no?
You can see the issue here.
Corte típica 45 grados en este caso, ¿no?
Like you can see, it's a 45 angle
También
degree.
está la resistencia al corte de la mampostería de adobe. Y
You
sabiendo
can see the resistance here of the
el
adobe,
mecanismo
and seeing the mechanism and the issue, you can calculate
un estimado de cuánto es lo que
and
estas llaves
estimate
resisten antes de
how much
este
resistance these keys have
y eso es suficiente
before they separate from the adobe wall. And if it's enough to maintain these adobe walls connected during an earthquake.
finalmente el otro
And at the end,
ensamblaje tipo B
you can see the assembly, the type B assembly, and you can see that there are also issues, but it's not symmetric. The key mechanism isn't symmetric. So you can see that it's more difficult to study the issue. And here you can see that on one side it's like this, and on the other side it's actually different. We can see here that in the case of the assembly A, it resists about 25 kilonewtons. And it's a uniform behavior. And in this types B and C, it resists about 35. It's a small increase.
Que es visible, ¿no? Visible hacia afuera, unas espigas o unas llaves de madera.
You can put some wooden keys that probably would affect the architectural aspect of this kind of building. Here you can see the different numbers that we obtained and the average. You can also say here the different efforts by doing a study. And clearly what you can see, what is closest to the type A, it has a way of behaving that's a lot more predictable. And the conclusions are the ones here, is that type A and on the section W1, if the demand is enough, to be able to separate both walls. So the general conclusions that you can see here is that all this information is a lot of information that was generated with these different studies. The idea of this presentation is just to encourage you to look at all the information in this publication, and that you are able to look at the numbers in more detail, because it can be useful for structural interventions for conservation in these type of constructions. When we look at the traditional structures, we can see that they are effective to maintain connections between different walls, but also to maintain the behavior of these structures. These pointer keys are useful. With this, I would like to thank you for your attention. And now Pablo Lorenzo will be presenting 3 publications related to the structural analysis of prototypes that we have mentioned.
So I'll show you briefly the work that we're doing and the publications that have been developed within the SRP project, which involves several of my co-workers. Basically, 3 publications are available in English and in Spanish. And as you can see from the titles, one focused on recommendations for advanced modeling. This is a type of modeling that is usually accessible for advanced engineers with, let's say, training after a regular education of 5 years. Then the second publication provides results from the 4 prototype buildings that have been discussed already. And the final publication tries to be of use for designers and for easy assessment, mostly by hand calculations or simplified analysis. I will start with a brief introduction by the fact that the built heritage is at risk and the hazards can be constant, can be natural, man-made, but can change also. Not only the power of destruction is increasing, but also climate change is an issue. Now, earthquakes are not the most costly disaster, but are the disaster that kills more people every year. And most of these deaths are due to masonry and earth buildings. And the reason for this, I'll show you a couple of videos, is that existing buildings, here you see a building made of clay brick, which is basically 2 retaining walls and 1 facade. It is built on top of a moving table that replicates an earthquake. And as you can see, the failure was extremely fragile. And so basically, you can see that the top part is going to fail as a sort of V shape, the tympanum or the gable. And initially, let's say almost the entire part of the building collapses together with the back wall, which has an opening. And the opening is also weakening the wall. But not the whole gable collapses, only a part. Then subsequently, as the earthquake, let's say, progresses in time, another part collapses, and you end up with this pier, which with a little bit more of energy would also collapse. And so existing buildings are normally made with materials that are relatively fragile. This is the case of earthen construction. They are quite heavy, and they are also inadequately connected. And so if you increase, and this is a similar building, which is subjected to a large earthquake, again, the earthquake is towards the screen, and as you can see, we have nothing. And so an earthquake will typically kill the people inside and kill the people outside, or people trying to exit the building. In any case, these buildings can be relatively easy repaired. And as you can see here, this is a repaired building, which is also masonry. In this case, it's stone masonry. And basically, the floors have been connected to the walls by steel ties. And this provided this box behavior, this integral behavior that also Professor Torrealba was speaking about. And so most existing buildings collapse in a real local way. In a lot of cases, the material is of very poor quality, as you can see also here. And as a consequence, you lose part of the material, but collapses are mostly local. You can see here collapses of cables, collapses of corners, collapses of parts of buildings which are improperly connected, and collapses of facades. So most of these buildings collapse out of plane, and they are quite destructive with local failure. And so typically, as it was done in the church already shown in Peru, the objective is to avoid disintegration and to ensure connections. And now these three publications try to address this. And so in the first publication, basically, the recommendations are for advanced modeling, I would say for experienced users, advanced users of sophisticated codes, mostly on the nonlinear range. So the most used approach to model these complex buildings is the finite element method. And basically we discuss the methods, we provide some guidance, we provide some recommended properties, and we provide two application examples. One is a test carried out at PUCP in Peru, and the other one is one of the case studies. And so basically what is done in this first guideline or report is to discuss the possibility of analysis, both applying the earthquake in a static way, let's say forces which do not vary in time, or apply in a dynamic way. There is a discussion on difficulties or problems in using this type of codes. Things like what are good representations of elements, which are bad, where do we have to have a better representation of in the model, or we can have a less detailed representation. An example here you can see of a building which the volts are represented and which the volts are not represented or are approximated with very different performance. So it tries to guide the user on using correctly these advanced tools. Subsequently, there is a discussion on the properties that need to be used and the material models. Two well-known softwares are presented and discussed together with the material models that they are used. They are compared, and you can see that an advanced user, by using different softwares, should get comparable results. And then there is a discussion on the properties that can be used. And so different codes are used, are shown, examples from the New Zealand code, examples from the Italian code, the American code. Also, well, these examples, let's say, consider masonry, both brick and stone, because normally masonry is also present in earthen construction as a base, as a plinth, or as a pillar, as a column, but also recommended properties for masonry for earthen structures are given. There is an extensive review of the properties that are found in literature, and then values are recommended for application in these advanced computations. Then two applications are provided, two application examples, as I told you. One is this shaking table test carried out at PUCP. So here you can see the results of the shaking table test. And this is the result of our numerical simulation, which fits quite well the envelope of the tests in the shaking table, and also the failure mechanism and the areas of damage, which are here indicated by the green and the blue color, somehow replicate the damage pattern that was observed in the test. Second example shown is the Cunhutambo church that was presented before. And so the example, the finite element model, the computer representation of the building is shown. And then the building is taken to collapse in the computer. And this occurs with these large cracks that you can see here in red. So this is an indication of cracks. This clearly indicates that the building collapsed with a local damage. In this case, it's only one of the facades. And by looking at the damage that we have in the building and the cracks that we find in our models, it also provides some validation for the simulation. The second example, the second report which is given is on modeling the 4 case studies. And so basically you'll find a brief description of the case studies, a discussion on the modeling. Then 2 of the case studies are discussed both on the unstrengthened and the strengthened configuration. The Church of Santiago Apostol do Cunho Tambo has been already strengthened. The Ica Cathedral will be strengthened, hopefully in the very near future. And then 2 of the case studies have not yet been strengthened, which is Casarões and Hotel Comércio. And so basically what is shown for the 4 case studies, and only 1 is shown here, is the performance of the building without strengthening. And here you can see again in red what happens in case of an earthquake. And so these are the cracks that if the earthquake is sufficiently strong, will develop in the building, which in this case will mean this facade will collapse to the back, this facade will collapse to the front, together with also here the presbytery, and here you can see the sacristy and the facade of the wall, or the collapse of the side walls. And so here you can see basically an indicator of capacity. This line indicates grossly the requested capacity according to the Peruvian code, and you can see that the capacity of the building was insufficient. And then we have the same building with strengthening. And so the strengthening was defined by Professor Daniel Torrealba with cooperation of University of Minho. And here you can see the actions that were made in the building. You can see a very complex building represented as a computer simulation with the strengthening. And you can see the damage of the building when the same is subjected to an earthquake. And the major difference that you can see from the past slide and the new slide is that this damage is extremely localized. So depending on the direction and let's say the magnitude of the earthquake, part of the building will collapse, but it will be only a part. Whereas after the building strengthening, let's say the damage, if the earthquake would be sufficiently large, would be very distributed in the building, and full collapse is not to be expected. So what was shown was that by applying strengthening to the model, it was possible to reach a capacity in line with what is, let's say, recommended or required by the Peruvian code for design of structures. Then the final report is a report on simplified calculations. This report should be of use, I would say, for technical architects, for standard engineers with an education of 5 years. And basically, different approaches are provided. They are all very different and they try to address different problems. And so again, there is a bit of discussion on material properties. Then there is a discussion of a simple method based on the, let's say, on the blueprint of the building or in the plan of the building. Then another method that is provided is the modern way of assessment and designing strengthening in most of these type of structures, which is based on the failure modes observed and macro blocked. Some discussion of the simplified use of finite element modeling, and some examples of design calculations. And so basically, again, a discussion on properties is given. So for different types of materials, what are the properties we can expect? These are coming from databases, mostly in Europe. In fact, important aspects when we discuss strengthening is or condition is what happens if the masonry is of better quality, or the stone is of better quality, or the earth is of better quality. And so there are factors that multiply the properties that try to consider the condition of the material by observation. And there are also factors that affect the material properties according to the type of strengthening that we can apply to the buildings. There is also presentation of a more advanced method that tries to consider with a little bit more of detail what could be a good masonry or a bad masonry. And here you have examples. So these are methods based on testing, on multiple tests. And here, for example, we can see what could be the quality of masonry according to different factors. And I show you here two factors. One, this is a cross-section of a masonry wall. For example, in this masonry wall, you can see that these two leaves are totally separated, meaning this factor is very low. Here, there's a little bit of interlocking, here interlocking, and here, meaning this factor is higher, and here there is excellent interlocking. And so I have a single leaf, whereas here I have clearly two leaves of masonry that will separate when there will be a strong event. The same thing for plan. So this is a cross section on top. This is a front view, a plan, or a front view. And here you can see the same. So a bad quality masonry where there's very weak interlock or overlap between the subsequent series of units. And so this value is low. And here you have a better quality. Obviously, this would be even better, but you have a better quality where there is more interlock between the stones. And so this is about material properties. A second, let's say a first analysis method, very simple application, is what we call looking at the plan of the building. This is the example of a church plan. Here in green, you can see the parts of the building that would respond if there would be an earthquake in the longitudinal direction of the church. And so if we sum all these areas, for example, we can have the idea of how much of the plan of the building is occupied by the walls in this longitudinal direction. And so typically you can see here for, let's say, medium seismicity, moderate to high seismicity, we should expect an amount of walls of about 10%. And so these are very simple indicators to tell us if the building is really unsafe or looks very, very unsafe and we need to do a more careful study, or if the building looks more or less safe. So this is important if you have, let's say, a city center, or if you have to assess many buildings at the same time. There are other indexes that are detailed in the report. You can see an example of what happens, for example, for a church, typically in the longitudinal and transversal direction. The transversal direction is normally the weakest, and you can see that more buildings fail when we apply this to many buildings. This does not mean that the buildings are unsafe. It means we have to study better. Second method that is shown is this method of macro block limit analysis or assessment, which is based on observation on how these buildings fail when there is an earthquake by local out-of-plane failures. So basically what we try to do is we look at the failure. It could be in plane, most of the cases out of plane. We define a mechanism and we analyze this mechanism in a simple way. So if this is my mechanism, I can assume it is equivalent to, let's say, to a single block. We can see that this single block, as it starts to rotate, this horizontal force is lower because this height increases and this height decreases. So the weight is stabilizing, the earthquake is destabilizing. If the block rotates, there is a lower force. And if the block rotates up to the center of gravity, is aligned with the rotation axis, then this force has to be zero, because the weight produces no stabilizing effect. And so this provides this law that you can see here. And we are able to assess the safety of the buildings in terms of this capacity law, in what we say in terms of forces. We can convert this law to a single degree of freedom by applying some factors and represent this in terms of dynamics, and then we make the safety assessment in terms of displacements. This is also given in the report, and it is applied for the Church of Cunhutambo by considering the original configuration here and different studies on using 2 buttresses, 3 buttresses, and 4 buttresses to see when it is safe. And here it is not safe, and here it becomes safe. A very interesting example, which is shown also in the report, is the need of connecting. And so if I have the original wall and I make a buttress and I do not correctly connect like it was done in Cunhutambo, then these 2 elements separate. And so this is safe, this is totally unsafe. And it is also shown in the report that it is unsafe. This is an example of a church that was strengthened in Peru incorrectly. So without connecting properly the buttress to the wall, and the result is separation and a bad response. There's also a discussion on simplified finite element approaches by using linear analysis, linear elasticity. What can we get from this? What can we expect from simple models, and how to apply and do some substructures of a complex structure to get information and to try to define and, well, to make a decision on strengthening. Then there are 2 examples of calculations, which are the final examples of this report. One example is the discussion of possible connections, for example, in an adobe house, by just connecting the walls, by connecting the roof, by connecting the floor, or by connecting everything. And examples of calculations of the collapse mechanisms and the safety you can see here. For example, this adobe house, which you see here, if the connections between these walls and these walls, the transversal and longitudinal walls, do not exist or are weak, we have a disaster response. And so you can see the capacity is very low. If I connect properly the walls by using the corner keys or ties, the capacity is multiplied by 5 or 6. So this simple, extremely simple action in the building provides a huge difference in response. Second example which is given is in Ica Cathedral, which again is the same idea. I have this facade. I'm going to connect the facade to the inner timber structure. In this case, the forces are quite high and a steel tie is going to be used. And so I have the Ica facade before strengthening. I have the Ica facade after strengthening. I require a force to stabilize, which has to be transferred to the timber system. And you have full details on the design calculations. For example, for the yielding of the tie, for the crushing of the adobe masonry, or for the cone response of the adobe masonry with the detailing or the final solution to be implemented. So in conclusions, I try to show you very briefly the 3 reports that we made for the Getty RSAP project. The reports demonstrate that there is a wealth of information. They are available in 2 languages. And well, we believe they are helpful to carry out safety assessment and to design strengthening. The final note is, well, these buildings, we have to ensure that they do not disintegrate, as we see in many earthquakes, and they are properly connected. So thank you very much. I give the word now to our host, Lucho.
Thank you, Paulo. I would like to thank all the panelists for Susan McDonald, Laura Cancino, Daniel Torrealba, and Daniel Lorenzo. We would like to remind you that you can ask your questions on the Q&A icon at the bottom of your screen. And here you can see the questions and answers Q&A, and you can send your questions here. Now we have received some of them. And I would like to leave you with Alexandra Sberga, who will present the questions that we have received and that we will probably receive now. Alexandra.
Gracias, Lucio, and thank you to
Thank you.
everyone that submitted the question. I'll start with the first question to Claudia, and is in the Cusco earthquake of 1656, which material are the church or cathedral domes made from? I think it refers to the paintings that you showed before. Thank you.
Thank you, Alessandra. Yes, what happened in Cusco is that a lot of the churches that were built in the historic center specifically, they were built in stone and brick, and that didn't change after the 1650 earthquake. And that has to do with the fact that, I mean, if you all go to Cusco at some point, you're going to see that the churches that are in the historic center are actually very confined. They are not like isolated, like in the landscape. They are confined by other buildings. And I think that has helped during seismic events to avoid the total collapse of the walls and the domes. So I think, so the answer is that the materials didn't change in the case of the churches that are within the historic center of Cusco, but it has to do with the fact that they are confined. So it's like they have like really big buttresses on each side.
Thank you, Claudia. And also the second question is for you. And as you mentioned, the Getty Institute has been working alongside with the Ministerio de Cultura of the Peru. And I've been used a different evaluation system, like the use of thermocamera. Have any of these innovations been adopted in Peru for the analysis of conservation of historic buildings?
Yes, I mean, we have been working with the Ministerio de Cultura for a very long time, and we have had like a really excellent collaboration with the Dirección Desconcentrada de Cultura of Cusco. We actually brought the thermocamera at the beginning of the project, and as well as, for example, we have also bring some total stations and laser scanning. And we have actually developed some workshops as part of the implementation phase of the work done in Cuñotambo. So it's not only that our colleagues from Cusco have been able to adopt the evaluation techniques, but also they have been trained on how to properly use them. And I think that's also part of the capacity building that normally the GCI brings to all of its projects. So yes, they have been used on site, on different sites.
Okay, thank you. I'm going to read like the third question for l'ingeniero Daniel Torrealba. So, usted define que la resistencia es sobre todo el mortero, siendo así una iglesia de mampostería de piedra y mortero de tierra.
You can say that structurally it works like a building of stone or adobe. There are many structures that actually look like they're stone, but they are earthen or adobe. It's more like a earthen structure. What happens is that stones in general are very large. So when we lose the mortar because of different effects, what is left is the interaction between the different stones, and this creates some resistance as well. It's not really a stone structure. If we were able to do a test, we wouldn't be able to compare between a stone and adobe structure. But if we were to do a study of resistance to the cut of a stone structure or of adobe structure, the difference wouldn't be very big. From that point of view, it's more like an earthen structure.
Perfetto, gracias.
Thank you.
Creo que the following question is for Engineer Paolo Lorenzo. If the foundation of the cases presented showed some problem as well than the walls.
Okay, thank you. In fact, I think it's for both of us, also for Danielle, but in any case, in our models, we did consider in several cases, because we did in situ testing both for materials and for the structure using dynamic identification. And it was clear that the foundations, for example, of Cunho Tambo were not in good condition. And so not only we consider this in the model, but also the foundations were extensively repaired by rebuilding part of the same. In this case, it's I believe most of it's made with stone masonry and with stone and earth.
Bueno, complementando la respuesta, yo
To
separaría.
complement this answer, I would separate this answer into if there are problems with the foundation where the structure is, I don't really think there is a problem or proof that there would be problem in the foundation, but there are other aspects that we have to take into consideration, like humidity that comes from the ground, especially in Lima. And then in churches, we have to take into consideration the erosion of the ground on which the church is built. And through this erosion of the structure of the churches was through this erosion of the climate on these structures. There are problems of humidity, and there are problems that come from the erosion of the land.
Thank you to both. The following question is, there has been a discussion of the use of external fabric reinforcement over earthen masonry. Have any recommendation been developed for the use of external reinforcement? I don't know if Danielle and Paolo wants to comment on that.
By external reinforcing, no, well, external reinforcement, I understand something that is applied on the surface of the masonry. And in this case, perhaps we are talking about the geogrid or something like that. Or external reinforcing that also can be understood, can be understood as the connections. For example, the tie beams. Tie beams are external, applied externally to the walls, right? So tensors are also applied externally to the walls. Then, in both cases, yes, both techniques has been implemented in the restoration of the Cunho Tambo church. But this is what I can say.
Yeah, maybe I can add a little bit. I mean, I think the question was, at least the first part was on external fabric reinforcement. And so the concept were more on meshes, I believe. In both in Cunhotambo and in Ica Cathedral, it was planned to add some gel grids. No, so this is made with, let's say, with a polymer which is stretched in order to increase the stiffness, which is often used, for example, in soils. And there's a wide experience in Peru, and I believe there is even a manual that Professor Torrealba developed in Peru. In any case, we have done works in the past also with natural fibers. I would say that for very large structures, like we have, if we're talking about walls of 1 meter thickness, 2 meters thickness, the external reinforcement, in my understanding, should be more understood as a container that does not allow the building to disintegrate and to collapse and kill everybody inside, then to provide additional tensile strength. Because in a very thick wall, the additional tensile strength provided by an external fabric reinforcement is, to my understanding, is marginal. So it is mostly for preventing full disintegration.
Thank you. And the following question is, I think Claudia can answer to that. I'm going to read. Vemos que se han hecho una serie de aportes importantes.
We have seen that there have been some contributions about building an adobe. What other information has been given for these contributions?
Previous question. I just want to remind everybody that our final outcome of this project are the guidelines. So the guidelines are going to have, some of the details of how those techniques are being implemented or could be implemented. So that was also going to be the ultimate dissemination tool of the results of this project. But also something that the project has done while the work at Cunhotambo was happening, we developed a series of workshops. I think we had a total of 5 workshops that were given to our colleagues in Cusco that explain the methodology of the project and how the design and the testing, the modeling, and the design of the construction drawings were developed for Cunhotambo. As well as some workshops regarding the documentation of the site, as well as in the case of Cunhotambo, specifically how we address the consolidation of the wall paintings prior to the structural or the seismic retrofitting of the church. So normally the Getty has like these publications that we are promoting right now, but then we also develop sort of capacity building and dissemination workshops of the results of the project. And we plan to do the same for the implementation work that's going to be carried out at Ica Cathedral. And this time the workshops are probably being open to a Latin American audience, not only regional colleagues.
Perfect, thank you. The following question is for el ingeniero Torrealba. Y en la catedral de Ica se ha identificato el tipo de madera en su estructura.
The cathedral, what kind of wood do you use? Because there are different types of wood, structural and non-structural.
Como mencioné en el Hotel Comercio,
as I mentioned, they identified cedar, pine, and another called sapel in Spanish. For quincha, as we called new quincha, we used another kind of wood. And when we used the panels for the quinchas, we took it apart and built it back together. We used the original wood. In this case, it was cedar or a pine. We used the original wood. But in the case of the new studies, when you do a study, you have two options. You want to know how the original system works. And for this, you have to reproduce the original structure with new material, using the same material, wood, cane, etc., etc. And this way, you can see how this structure works and how it was thought out originally. And then you have to look at how something deteriorates over hundreds of years. That is what we study as well when we extract and take, for example, a wall, we take it apart in the lab and put it back together. We see that 30% of decrease, but and then the capacity of movement is practically the same. And this is what we want to see when there are earthquakes. Thank you.
Question is for Claudia and Daniel. I'm going to read them. ¿Cómo los estudiantes de ingeniería y arquitectura?
How can the engineering students and architecture, how can they be involved in these initiatives and studies? Thank you. Currently, when we look at the Masters of Civil Engineering, when we look at the classes in that master's degree, we see and we show the concepts of the structural intervention. Currently, we share the information that we have generated in these projects, and we show it to the students. And when we look at the courses that are for bachelor's degree, these are elective. Even though we do them yearly since 2011 or 12, but now these subjects are not dealt with, but they are dealt with in the master's degree.
First of all, I think in the School of Architectures in Peru, as for many years, there has been a course on earthen construction that I think is very important for the students of architecture, but also some universities like the Universidad Peruana de Ciencias Aplicadas has a course on conservation that is actually taught by one of our consultants who actually developed all the beautiful drawings that I have shown you of the 4 building prototypes, that is the architect Mirna Soto. And then also there is only one master degree in historic preservation in Peru that is from the Universidad Nacional de Ingeniería. And I think I will encourage all the other universities to actually think about a master's degree in conservation, knowing that the vast amount of heritage that Peru has. But so far we only have one master's degree.
Thank you, Claudia. The following question is for all the panelists. Una de las principales complicaciones en la elaboración de propuestas de reforzamientos es que se suele exigir que la estructura...
What happens is these structures are with these modern type of norms, and then would make interventions. And it's, in your experience, how can you find a intermediate point with all these customers, with local entities to have a safe intervention and would go abide by local codes. This is done through knowledge. Knowledge that has been generated in this type of project, right? It's a source, a very fundamental source of support to say that these levels of security have been able to be achieved with these interventions would be enough in order to be able to obtain the security levels equivalent to the ones that the norms require. This has happened in the Cuñatambo church, and Dr. Pablo Lorenzo mentioned it. And this can also be applied to other type of interventions for other types of monuments, other buildings.
Yeah, and I also would like to add to this. I think one of the things that we have tried to do since the beginning of the project has been that we try to engage the authorities and the local community right from the beginning. So it has actually happened that, once the authorities start looking at the results of these studies, they actually get sort of convinced on the safety and the science behind the proposal that we are developing. So I think what Daniel is saying is through knowledge and the dissemination of knowledge and the engagement of the different stakeholders, I think it's much easier to be able to develop a proposal that sort of follows within what the code requires.
Maybe if I can also add just a short comment. I mean, I am not sure about the situation in Peru, but in Europe, it is clear that for existing buildings, the level of safety is lower than for a modern building. The reason is evident because if the building is there and it already, let's say, has been there for a long time, and the cost of an intervention is always much higher than to implement or design and to make a new building. From the point of view of risk, for a standard building, it makes sense that the safety level is slightly lower. So typically, I would say that in Europe, normally for an existing building, when we think about earthquakes, let's say the demand is about 20% lower. And normally you are only forced to do strengthening if you don't reach like 90% of this value. So there's about a 30% reduction if you have an existing building, which is purely from the risk perspective and the cost of the intervention. Now, the heritage buildings are never considered. And so heritage buildings, I believe across the world, they are exempted from complying with the codes. This does not mean, in my perspective, that we have to assume that heritage buildings should be unsafe and people can use them if they are improperly, let's say, assessed or strengthened. So I fully support the other colleagues that knowledge is the answer.
Thank you. Unfortunately, we are running out of time, so we have time just for the last question. But once again, thank you everyone for submitting your question. And the last one is for Paolo. I'm going to read it. ¿Cuáles serían las tendencias para el modelamiento estructural de edificaciones?
What are the tendencies for historical edifications using artificial intelligence, maybe? As far as the future direction of the modeling, structural modeling, that is a very...
I would say that, it is important to understand this process from two perspectives. One perspective is research-based and the other perspective is engineering-based. And so from the research base, often we are doing very complicated procedures. For example, consider the internal structure of the materials, and the randomness of this internal structure and the randomness of the properties. Dynamics will remain always a problem, and so there's many things we need to do better from the point of view of representing the action and having the response of the structure. From, I would say, the professional point of view, we have now stabilized analysis tools for buildings that have an integral or box type behavior, so tipo caja. But this is not the case of most historic buildings, where you need, I believe, still adequate tools to define collapse mechanisms and to incorporate this in a sort of more automatic way for the designers. And so there's many challenges. I think there's many people across the world, including Peru and obviously all the countries addressing these issues. The step to making this easier to use for professionals is a difficult step sometime. I have mixed feelings about machine learning techniques and artificial intelligence, because too often the responses are constrained by your data. And so if your data is insufficient, your response tends to be crazy. And so I think this is still a long time ahead before we can use it in historic buildings.
Thank you, Paolo. And I'm going to ask to Lucio, to give the floor to Lucio, and thank you to everyone for your answer and this amazing discussion.
Muchísimas gracias a nuestros panelistas por haber.
Thank you very much for our panelists to answering these questions. You'll be able to see in a moment the link in your screens that you would be able to download all these publications that have been presented today. In the meantime, before I say goodbye, you could see all these publications in the bottom in the link where you could access in the webpage of the Institute Getty. Before I say goodbye, I want to thank Getty Audiovisual, Getty Digital, and for the organization, for Elizabeth Pat and Dr. Alessandra Spiga for her participation in the coordination of this event. Thank you very much to all of you, and I hope to see you very soon in our next opportunity. Thank you from the Getty Institute and the project. Thank you very much. Good morning, good afternoon, and good evening.